So thanks for the expectation management, Mike. Now, I have to confess that actually I was originally setting up in the overflow room to avoid the crowds, but the organizers were on to me. So nevertheless, I'm still happy to see you all here. Welcome to Edmonton, and thanks for joining. Now, you might notice already that this is going to be an outlier talk. Notice the absence of the word reinforcement and learning. There will be reinforcement learning in this talk, but I better share the plan first. So in fact, what I'm actually going to do is, for the most part, focus on large language modeling with a particular take on it. I'm going to focus on large language models as general purpose computers of the type we're actually familiar with. And so the first thing I'm going to do is present some theory to actually make that concrete. But the main purpose there is to allow me to frame the second part of the talk, which is I'm going to use that as a means to express some of the challenges that we're facing in trying to drive these models to be better reasoning engines, and some of the computational issues that are coming up that are not being properly addressed by sort of standard machine learning approaches and standard machine learning thinking. Finally, in the last part of the talk, yes, there will be some reinforcement learning. This will be the most delicate part of the talk, but at that point, what I want to sort of explain is reinforcement learning indeed does overcome many of the challenges that I'm going to point out in part two, but not entirely. And so through this talk, what I'm mainly hoping to do is not really offer solutions as much as try to give you some perspective or some sort of, I don't know, my best attempt at a clear framing of the issues so that we're not attending so much to questions that are really, I would say, distractions, and trying to focus on, I think, questions that are really going to chart the way forward. Anyway, that's a bit ambitious. We'll see how it goes. So let's see. Okay, so part one, language model as a computer. And this actually often strikes people as sort of a strange thing to say, because we all know where language modeling came from, right? It was just this, endeavor to sort of, capture human natural language behavior, usually in the form of text, which, over the years wound up being kind of crystallized into this very simple idea of building a conditional probabilistic model that has expresses a conditional distribution over the very next symbol or token or word, or maybe a sentence, given some finite length context string. And you might ask yourself, what does this have to do with a general purpose computer? And to answer that, I'm going to sort of share when this became clear to me. And for me, I started to see this connection between language models and computers right at the dawn of this so-called chain of thought phenomenon. Okay, so you all know the story, but I just have to set something up here. So at that time, we were looking at these GSM-8K problems, these math word problems, the kinds of word problems you got like in elementary school or junior high. Things like, Janie got 2 apples from her mother, twice as many bananas from her uncle. How many fruit did she get? And when we're trying to get the models to respond, 6, okay? And then there was this kind of remarkable discovery that if you just simply took these question answer pairs, say in GSM-8K, and just interposed between the question and answer just a natural language expressed semi-coherent reasoning chain, like Janie got got 2 apples from her mother, twice as many bananas from her uncle. How many fruit did she get? Well, she got 2 times 2 equals 4 bananas from her uncle plus 2 fruit from her mother, that equals 6 fruit. The answer is 6. So we just simply add this reasoning chain between the question and the answer. And frankly, we were stunned. This was like a step change in the performance of these models. They went from like teens accuracy up into the 60s, up into the 70s, almost overnight. Quite shocking, okay? However, that's not the real lesson. So the real lesson comes from actually understanding what were we doing before this, okay? And what we were doing before this is good old-fashioned machine learning. You literally take the GSM-8K data set and you treat it like, like a supervised learning data set. You have a bunch of question-answer pairs. Here's a question, here's an answer, da-da-da-da-da-da. And you wire up your big neural net or your language model, and just by, gradient descent on log likelihood of the answer, you just try to optimize the probability of eliciting the correct answer on the training set, and then test on a holdout validation set, okay? And what we were finding before this chain of thought thing happened is it didn't work, okay? It didn't work at all. We were seeing accuracies on this data set, down around 10%, 9, 7, 11, stuff like that, okay? Now, the real lesson here is actually, it's not just that it didn't work, it couldn't have worked. There was no possible way for this to have worked. And the main point I want to make, and one of sort of the main points I want to kind of get across in this talk is to understand why there was no possible way for this to have worked. And to understand why standard supervised learning could not have solved GSMAK, you have to think as a computer scientist, not as a machine learning researcher. So what do I mean by this? So as a computer scientist, what does it take to solve a GSMAK problem? Well, these problems, they're not too hard, but at their core, really what they are circuit evaluation problems. That is, all of these word problems, what they'll do is they'll set up a bunch of variables that happen to have values, like quantities, and it'll express a bunch of arithmetic relationships between those quantities. And then so you build that circuit, and then you evaluate the circuit to calculate the final answer. Okay, and yeah, there's language involved in trying to recover the the quantities and the variables and the relationships in building that circuit, but you still have to evaluate that circuit. Okay, now as a computer scientist, what would it take to do something like this? Well, it's not a hard problem. Circuit evaluation is not too hard, but guess what? Circuit evaluation is a linear time computational problem. It takes time proportional to the size of the circuit to calculate that final value. Okay, straightforward point. What were we doing? What we were doing in trying to do supervised learning is we were trying to update the weights of the model to basically in one pass through the transform, or more precisely, like through the first few tokens to give the answer, to completely solve the circuit, to build the circuit and solve that circuit evaluation problem. Okay, this cannot work. It's an impossibility. Okay. Another appeal to your computer science background is, when in your experience have you ever written a program that operates as follows? Program starts, reads input string, and without doing any intermediate calculation whatsoever, starts printing the answer. This is known as constant time computation. Okay. GSMAK is not a constant time computable problem. It's a linear time computable problem. Lo and behold, if you take a constant time, computable architecture and try to train it to solve, to answer these questions, it can never work. However, as a machine learning researcher, what does it look like to you? Well, it's going to look like an out of distribution generalization issue, right? You will fit the training data, guaranteed. These models are massive, okay? You fit the training data and you go to some holdout, test questions, and it's not working. And so as a machine learning researcher, you respond by saying, ooh, these test questions are bizarre. They must be out of distribution. So we have to somehow get more coverage from the data. Well, guess what? If you're trying to compile a linear time algorithm into a constant time budget, there is no coverage issue. You could get data forever. This will never work. It's not a statistical problem. It's a computer science problem. Okay, so finally, to sort of end this story, the real lesson from this early study is that if you want to solve linear time computable problems, you need to give the language model a budget to express at least linear time computations. And this was a game changer, okay, overnight. All right, so, okay, just first point, just to kind of warm you up. So this is one of the themes I want to kind of come back to throughout. I've already created controversy, so this could be fun. Hang in there, it'll get worse. Okay, so now let me get back to sort of the main narrative I wanted to share, which is, we're all well aware of these, sort of narratives out there about, LLMs can't do this or they can't do that, or, blah, blah, blah. And I think these are very interesting questions, but actually I think that these questions are often misinterpreted even by those proposing answers. And so I want to help sort of clarify some things by first focusing on a much simpler, much more precise question. So instead of kind of getting lost in the weeds, philosophical weeds about whether a language model actually understands anything or actually can reason, how about asking a much simpler question, which is, can a language model compute? And by this, I mean something actually very concrete and very specific, which is based on the Church-Turing thesis. That is, can a language model compute in the same sense that your laptop can compute as a general purpose computational mechanism? And as long as you accept the Church-Turing thesis, we have a very precise, very simple definition of what it means to be a computer, which is a function and input-output mapping between infinitely many possible inputs is computable if and only if it can be realized by a Turing machine. okay? And of course, we don't have to fixate on Turing machines. You're well aware that there are many universal models of computation. We could equivalently ask that the function be realizable by a Python program or C++ program or a two-dimensional cellular automaton or a lambda calculus or a post system, on and on and on and on, okay? Now, what's important about these classes of models or machines is this key concept of a universal element, and this is one of Turing and Gödel's great insights, is that in these classes of machines, there exist universal elements, a single machine or program that can exactly simulate the execution of any other machine or program on any input forever, okay? And so this creates a very specific question, which is, are LLMs one of these, okay? And actually, superficially, the answer is, of course, no. It can't be. Why? Because we've sort of walked away from recurrent models, and we're now looking on transformer-based architectures, which, as you would know, have a bounded size context window. So the input-output map of a transformer, right, can only map strings up to a certain maximum length. Of course, it could be an impressive length, like 2 million tokens or something, but still up to some only bounded length, to render the next output token. So a transformer on its own is essentially a finite state machine. Now, very elaborate, very structured finite state machine, but it's just a circuit. Okay, so a transformer on its own cannot be a universal computer. However, if you just simply allow the transformer the opportunity to sort of continually, through autoregressive generation, or other nowadays thought of as chain of thought, inference, if you allow it that opportunity, you actually, in principle, maybe can increase its computational capacity. And the question is this enough? Would this give the transformer the ability, or a particular language model, the ability, in principle, to simulate any algorithm on any input? Now, before I move on, there's a small technicality, which is one of the mindset changes I have to get across is that when we're talking about models of computation, you are not allowed to bound the size of the input problem. If you think about any algorithm you've ever really designed, unless you're really deep in the weeds in some empirical algorithmic endeavor, any algorithm you've been taught or designed is designed to apply to all instances. It sorts all lists, no matter how long the list is. It adds all numbers, no matter how big the numbers are expressed as lists. Algorithms apply, in principle, to an infinite set of possible instances. An infinite set of strings cannot have strings of bounded size. Okay, so that means if we're going to sort of try to understand, the ultimate computational ability of a language model, we are going to need to consider how do you get the language model to compute on input strings that are much bigger than the context window. Okay. All right, so, well, I'll kind of spare the suspense. It turns out this totally works. It's not even that hard, okay? You can easily show that existing language models, as they are right now out there in the wild, are easily, you're easily able to drive them to be universal computers in a classical sense, okay? And how would you go about doing this? Well, I like the approach of not being deep, so here's how we did it. So you just have to, just imagine for a moment. I give you, there's some computation we want to perform on mapping input strings to outputs somehow. And I give you a really long input string, much bigger than your context window. First thing you have to realize is, of course, at some level, you're going to have to look at the whole input to be able to produce the corresponding output. So you can imagine just taking your now small context window, even if it's 2 million, and ultimately sliding it through, right, this very big input string, because eventually you're going to have to read the whole input string, obviously. Question, though, is like if we look at this, every one of these positions in that big input string is a context for the language model. And given a context, that language model will emit some tokens. So as you're sliding the window through the string, question is, what do you do with the tokens that the language model emits? All right. And simple thought experiment is, how about simply append them to the end of the string as you go? All right. So we look at the first context, we generate some tokens, we append them to the end. Slide over, look at the next context, generate some tokens, append those after that, so on and so forth. Now, quite clearly, as we keep going, eventually, we're going to be reading, in the context window, the very same tokens that the model itself generated. And by the way, as a simplistic edge case, if the entire input string fits in context, this is standard autoregressive decoding. Okay, it's simply a generalization of autoregressive decoding to input strings that are bigger than the context window. All right. So, question: is this enough? Does this give you, in principle, the ability to simulate, any algorithm executing on any input? And actually, you could already anticipate it. The answer is, of course, yes. And it isn't even really that hard, to be honest. The thing that's kind of interesting is you don't need 2 million tokens to simulate universal computation. It turns out you only need a context window of size 2. You can show you need more than one, so that's interesting. But you need at least a context window of size 2, and then in principle, you can simulate any Turing machine. Okay. Now, actually, I'm going to run out of time. So the details aren't that impressive, really. You can just, by doing this append thing, you can create a circular queue and you can start rotating memory to simulate the execution of the machine. Anyway, there's paper, and you can ask me offline. It's not that complicated. Okay, but just to continue, here's something a little bit more concrete to make some progress, is that you, and I've done this, you can write a compiler that takes any Turing machine and compiles it into a set of rules that map context windows of size 2 to emit 1 or 2 symbols to simulate the exact execution of that machine on any input. But more interestingly, you can take particular Turing machines. And why would we be interested in particular Turing machines? Well, we'd like to take a universal Turing machine. And so one interesting universal Turing machine is this machine called U15-2, which is one of the smallest known, it's on the Pareto frontier of the smallest known proved universal Turing machines. It's a machine that has 15 states and has 2 input-output symbols. And for this particular machine, when you run the compiler, it turns out you get a set of 1,857 rules defined on a vocabulary of 249 symbols. Okay? Interesting. So, what might this have to do with language models, you ask? Well, now you can turn to your favorite off-the-shelf language model, like GPT-5, if it comes out next week or something. And then you can ask, is the language model, in principle, able to exactly execute each one of these input-output relationships? It's a finite set to check. Can it be done? So here's how we perform this proof. This would be a year or more ago now with Gemini 1.5 Pro, which was a public model, but out of date now. By just employing a very simplistic strategy. So all we did is we just literally took that rule set and we just gave it as a big system prompt. Okay, and then we just interrogated each one of the 1,857 cases and just check with 0 temperature decoding, random number seeds frozen, right? Will the model give the exact right answer for each one of the possible contexts? And you can run, it's a finite set of tests, and you can easily verify after a little bit of prompt engineering that you can elicit these models to exactly implement these rules, which implies they can exactly simulate U15-2, which implies they can exactly simulate any Turing machine on any input. Okay, okay, not that big a deal, but something. Okay, so from this, I think that there will be consequences. Okay, so now there's a lot of objectionable aspects to this construction. So obviously what's going on here is, to get the language model to exactly simulate a formal computational model, we heavily controlled it. We restricted the context, we restricted the vocabulary, we forced the machine to run this very specific small set of rules, okay? And all I'm saying is, yep, you can do that, all right? I'm not saying you want to do that. I'm not saying it's a useful, helpful thing to do, but you can definitely do that, okay? But now, when somebody, raises questions to me like, does the LLM, can an LLM reason? For me, I find that in a sense, it's a strange question because that is literally the same thing as asking, can a computer reason? And I'm not saying that's a trivial question, but like, are you asking, is reasoning computable or not? And it's like, well, it depends, right? There's a lot of undecidable problems in logic. Are you saying that? Or anyway, now, of course, when people say LLMs cannot understand or reason, they're not actually talking about the inherent computational ability of the models. And I'll come back to this issue. To come back to it, though, I have a few other side quests that I need to fulfill here. So here's another thing that I think our intuitions, or at least my intuitions, misled me for a while, which is these machines are universal computers, but there's so much expense paid to train them on like the whole internet of text data. Is that why it's a universal computer? Like somehow looking at all this human chit chat on the internet, we taught the machine to become a general purpose computer. And the more I thought about this, the more I started to believe is like, no way. Yes, there are textbooks on the internet. Yes, there's some like, algorithm descriptions and so on, but most of it's garbage. I don't know. I just started to really be suspicious that this was really playing a role. And so then we sort of endeavored to sort of answer the following question, which is the human natural language data relevant at all for realizing the computational abilities of these models? And I'm happy to share with you a finding that, in fact, training on natural language has nothing whatsoever to do with the computational universality of these models. Language is irrelevant for computation, okay? How was this shown? Well, this was actually a very clever idea by Alex Lewandowski and supervised by Marlis Machado and I, which was this following setup. It's pretty straightforward, which is literally take your random transformer, not trained at all, not pre-trained, not post-trained, just a random initialized model, and just learn a symbol remapping, okay? Using an encoder and a decoder neural net, that really all it has to do is take each one of these 1,857 contexts, take the symbols in those contexts, remap them into some sort of symbols that the frozen random model takes in, run it through the model, map it back to the same symbol set. And if you can train the encoder decoder, there's a couple of technicalities, but basically if you train the encoder decoder to exactly simulate each one of the rules, this is now a universal computer with a random language model in the middle, okay? And actually verified, Alex shocked me with this. You don't need a giant language model to get this work. In fact, it works for very small models, random RNNs, random LSTMs, random transformers, not even big ones. Now, it's not vacuous. If you get too small, you will start to fail, okay? So computational universality in some sense only requires you to exhibit a small finite set of behaviors. And, but if your model's too small to realize that small finite set of behaviors, sure, it won't be universal. But you don't have to be that big. It's only 1,857 constraints. You don't have to be that big to be able to exhibit arbitrary computational behavior. So what on earth is the point of spending tens of millions or hundreds of millions or heaven forbid billions of dollars training these large models on human text? What is the point of this? Okay, well, it is not about changing the computational ability of that model. It was a universal computer at the start. It was a universal computer at the end. Okay, obviously, what's going on with all of this, training on internet data, at least pre-training, is that we're simply trying to make the input-output behavior of this model make sense to us, right? You can now have a chat bot where you put in things that make sense to you and it responds in somehow human-like way. That's nice. So it is a way to basically take a universal computer and adapt its interface to be something that you can work with, okay? That's one of the key sort of consequences. I think the other key consequence is that actually there's a byproduct. Now, this is a bit risky. I won't dwell on it too much. But in addition to just being a natural input-output interface, it does this remarkable thing about capturing knowledge in the sense that, when you ask it factual questions about stuff on the internet, it seems to respond with correct answers sometimes, and distasteful answers and other times, and so on and so forth. But there's this weird byproduct of somehow apparent comprehensive knowledge of what all this human chit chat was expressing out there. Okay, I'll come back to that also later. Okay, so I want to wrap up this section because you're all getting bored of Turing machines, and we want to get to machine learning and reinforcement learning. But just a few sort of wrap-ups here. So, I typically, encounter this reaction like, who cares, right? Like, who cares about Turing machines? And moreover, I think as I've said already, it's not like computational universality is a super high bar, right? Really small models, as long as you have a small finite control that has access to some unbounded memory that it can operate on, it's pretty easy to get universal computation. This is not a high bar, okay? It doesn't mean that model's useful. It doesn't mean it's programmable by you or I, but it definitely, allows it in principle to perform any computational task. I think one of the main utilities of this, at least in my mind, is at least it prevents us from being distracted by a lot of, I think, the fairly naive questions that I still encounter fairly regularly. Like a question comes up like, can an LLM perform exact reasoning? In principle, of course the answer is yes, right? If exact reasoning is computational, then yes, you can exactly find some way to elicit that kind of reasoning behavior in the model. Here's another one that sounds fancier. For any computable input-output behavior, is there a prompt that elicits it? And the answer is yes, right? That's essentially what the proofs show. Now, it elicits it in a very indirect way. It's going to elicit it by writing a program that drives a Turing machine that simulates some other thing, right? But for any computable behavior, there is a prompt, big system prompt, that will drive the machine to implement that computable behavior. End of story. So I don't understand why we're hung up on some of these philosophical confusions here. Okay. Now, obviously, I'm not answering the real questions that I think are going out there, which is the questions are not about the ultimate computational ability of these models. The questions are obviously about getting the models to do what you want. And that's super hard. I could put it more kind of prosaically, which is nobody knows how to program these models. They're not formal machines, right? Output behavior is unpredictable to us. They seem to be useful and then they're not useful, right? It seems to be working and then it's not working, right? So we do not have a grasp on this sort of aspect of this kind of random and trained machine that we're now confronted with. So the key questions are not about ultimate computational ability. They're essentially software engineering questions. What does it take to interact with the model to elicit the actual responses that you're looking to elicit from the model? And this is harder than programming a formal machine in some sense because we don't really have a clear understanding of the input-output behavior of the model. Like it's a big transformer circuit, right? But nobody really understands that circuit. So I think most of the questions that we're hung up with are software engineering questions, and that, I think these are the important questions. Okay, well, I'm already offending people, but just let me keep going. So, just here's a picture that sort of helps me make sense out of where we are, which is there is a direct analogy between a classical formal computer as the type we've been trained to think about since for the last 80 years, and language models, with a twist. Right, so obviously there's a direct parallel between a formal machine, a computer, and a language model. There's obviously a direct parallel between a program and a formal programming language to drive a formal machine. There's a direct parallel to a prompt that or system prompt or some sort of background prompt that you would give to a language model. And then there's a parallel between the input to a program and the question you would ask to the language model. There is a parallel between the execution trace of a formal computer, just like, that's parallel to the chain of thought output autoregressively generated from the language model, and a parallel between the output and the answer. What's new now, and I think what's very exciting, is that we're somehow training the computer. We're somehow training the computer to be more useful. And you have to admit, it's actually working. But the slides are not. Okay, it's actually working in some sense. Now, some of it is a fantasy, right? Like, by training the LLM, we're going to get a complete free lunch where I don't ever have to write a program again and get all of my questions answered. No, come on, right? That's essentially asking for clairvoyance. It's a clairvoyant machine. It knows what I want before, I even approach it. Like, that's not going to happen. There are going to be some ultimate limits here, but it's remarkable already what we're seeing, right? So think about it as a computer scientist, right? In the formal model of computation above, if you want to solve a problem, what do you have to do? Well, you, the poor human, at least up until recently, you had to understand the problem, which is an infinite table of input-output pairs. And you had to write one finite description of step-by-step instructions to drive a formal machine to correctly solve every one of those infinite sets, every one of those infinite instances of input-output pairs. This is super hard. This is why we're specialists. This is why we have universities training people to write programs. It's a very difficult thing to do, okay? Now suddenly we have this weird democratization where everyone can just sort of chat with the model and somehow elicit it, to perform various computations. And look, I'll just be plain. We know what we want here, right? We know that this model has seen the whole internet, roughly, to a first-order approximation, which means even as a computer scientist, the model has already seen every data structure, every algorithm, every Stack Exchange article, every textbook, every strategy, every heuristic. It's seen it, okay? So what is the hope here? The hope would be if I come to the model with some sort of computational problem, I don't have to formalize the problem. I want to ask the machine the problem, can the machine recognize the problem and understand what's relevant to answering that problem? Like, ooh, you need a dynamic program, right? And then can the model faithfully execute that algorithm, say a dynamic program on that input instance? And here we can start to see the story falling off, okay? The fact is these models do know a lot. They know a lot more than you do about computer science and math and physics and chemistry and politics and economies and societies. They really do have that knowledge. But there's a lot of know-how that is still not tightly connected to the, a know-of that is not tightly connected to the know-how. So the model indeed, like if you go to any model now, it knows more about dynamic programming than you do, okay? It can express all kinds of versions of dynamic programming beyond your experience. What it cannot do now, though, is faithfully apply that algorithm to a particular input instance. And this is the gap that frustrates us, that feels inhuman. And I think this is one of the core technical problems that we're trying to get over right now, sort of closing this gap. And of course, the models trained on human text have all kinds of useless, distasteful, crazy stuff in there as well. Okay. All right, so now I want to move to the second part of the talk, which is I want to start to pivot more to sort of a machine learning stance, which is at least play along. Imagine you're trying to train the LLM or alter the weights in your language model to somehow be a more reliable execution engine or reasoning engine. Now, first thing to observe is by doing so, you are not changing the ultimate computational ability of the model. It was a universal computer at the start. Hopefully, it's still one at the end, okay? It is not about changing the computational ability of the model. It is about changing the behavior of the model to kind of be more usable by us, to be more directable by us, to be more sort of programmable by us, where the behavior it emits is kind of the behavior we were looking for or hoping for, or it was at least correct, even if we don't understand the algorithm, okay? Well, this is hard, okay? And the first challenge I want to put up is one of the reasons why I think it's currently hard is that a machine learning mindset, I'm going to argue, somewhat controversially, is not the best way to look at this problem. And this will harken back to the first example I gave. So one of the shortcomings of a machine learning mindset, right, is this idea that what we're going to do is we're going to look at data. And when you're looking at data, right, it's going to be some finite set of data. And we're going to take some massive model and we're going to somehow fit or optimize a massive model to that finite set of data. And one thing we understand about this, I mean, machine learning's been around a long time, statistics even longer, is that we can give some guarantees about this kind of endeavor, but those guarantees, for the most part, are going to hold in what I'll call in distribution, right? If I give you a bunch of finite set of data from some sample of behaviors or input-output pairs or whatnot, and we fit models to that data, we can give you some guarantees of some form about how that model will behave on other trajectories or input-output pairs from that distribution. What we're not able to tell you really very well is what is that model going to do on traces or examples that are quite different from that training set, okay? This is a problem because computer science does not think this way. Computer science is about the study of formal systems, as is mathematics, and the whole point of a formal system, the whole point of mathematics is to generalize out of distribution. That's what it's for. It's not about, oh, I can add numbers up to 3 digits. Like, no, you can add all numbers forever, no matter how big, okay? It's all about out of distribution generalization. And the concept of an algorithm in computer science is about solving all instances of a problem, not some instances some of the time, right? Well, I mean, there's some randomized stuff, but basically, for the most part, what we want are formal solutions, like formal systems, at least if we're computational geeks, okay? But this is a very difficult bar, very high bar for a statistical-based approach that's going to only analyze a finite set of data. And in fact, people have thought about this, for a long, long time, and way back, starting in the 60s, there is an endless sequence of negative theoretical results that essentially tell you time and time again, if you want to recover an exact formal solution from a finite set of data, it's hopeless. You will always find some problem instance and some data where you will fail, and you will not be able to control the reliability without astronomical to infinite data sets. Okay? There's just an endless supply of worst case theory telling you it's hopeless. So do we give up? And The interesting analogy I would give here is to computer science. So again, appealing to your computer science backgrounds is, it turns out actually computer science is hopeless. And what do I mean by that? Actually, proving an algorithm correct is undecidable. Almost all of the interesting questions about programs are undecidable questions. Semantic equivalence, undecidable. Any non-trivial computational behavior of an algorithm, undecidable. All of computer science almost up at, at this level of question, it's undecidable. So the theorists tell us to give up. No, what it means is you're not going to get a final solution. There isn't going to be a final assignment checker that compares semantic equivalence of two programs, a reference and a student submission. It will never exist. That doesn't mean computer science stops. Same thing here. Just because in the worst case, there's no way to absolutely guarantee you can correctly infer some finite algorithm from some finite set of data, it doesn't mean you stop. It just means there will never be a final answer. This is good news. It means there will always be jobs, well, at least for language models. Okay, so where I want to go from here is I just want to share a little bit more, down to earth eventually, some of the challenges that I've been trying to face and kind of overcome, and trying to get these models to elicit more and more trustable, more and more reliable formal system behaviors. Okay, so here's the first lesson I learned the hard way, which is if you're thinking about something like very concretely like a logical reasoning system, when you think about logic, what you're interested in is given a set of premises or assumptions, a sequence of conclusions. And there's a sense in which we want that sequence of conclusions to be logically correct, right? To correctly follow from the premises. The logical correctness of a reasoning chain, it turns out, has nothing to do, in principle, with whether or not the reasoning chain is algorithmically realizable. That is, algorithmic realizability and logical correctness are just orthogonal concepts. Okay, and by not sort of being aware of this, you can get yourself in trouble. So here's here's another way to explain it. So certainly, for example, right, if I can prove certain programs correct, right? So I can give you a training set of here's a program, and here's an argument that proves that program's correct. And here's another program, here's an argument that proves that program's correct. I can give you a finite set of these things, and you could try to train your machine learning model to prove correctness of new programs, okay? The upshot of this is it will never work. Why will it never work? Because that is an undecidable property, right? Proving correctness of arbitrary programs is not something that can be decided in general. You will have to restrict, like formal verification must have limited scope, okay? But you will never see this as a machine learning researcher. All you're going to see is I have a data set, I have my ambition, I fit my model to that data, awesome on the training data, and it's like, it's failing out of distribution. And again, right? And this will never stop. It cannot work. You will always fail out of distribution this way, okay? Now, let me bring it a bit more down to earth. Another version of this is I can give you like simple propositional logical reasoning problems, like say satisfiability problems, where I can give you traces of like linear time sat, right? Like here's a problem and here's a linear assignment of the variables that satisfies that problem. Here's another one, here's another one, here's another one. I happen to believe that P does not equal NP, which implies there is no algorithm that could solve this problem. Which means as a machine learning researcher, you can definitely train on data like that, but it will always fail out of distribution. It must always fail out of distribution because that big transformer circuit is a circuit representation of an algorithm. When no algorithm exists, you cannot succeed, okay? Now, let me bring this down a few notches to something that's even more tangible in the realm of linear time computation. Even in linear time computation, it turns out we're in a lot of trouble if we don't have our wits about us. And the way I prove this actually is just by a simple demonstration. So here's a simple demonstration of a propositional logical reasoning problem. So I'll just give you a bunch of propositions in the form of implications, like not x5 implies x3. What is it? Not x3 implies x9, so on and so forth. Okay, give you a bunch of implications, and then I'll ask a question. Does x1 imply x6? And sorry, I'm just noticing the time. I got to speed up. But anyway, does x1 imply x6? And obviously, actually, what I'm describing is a directed graph, right? And the question I'm asking at the end of the day is just a path reachability question in a directed graph. Okay. Now, as a computer scientist, what does it take to solve a problem like this? Well, if I'm thinking as a computer scientist and want to solve a path reachability problem, it's not completely trivial. It's a search problem, right? In principle, I need to actually explore from the start vertex, at least that's one way to go about it, to see, is there a directed path to the target? Because there may not be, and ultimately I'd have to explore a whole connected component to prove there is no path. Or maybe I stumble into a path. One thing I wouldn't do as a computer scientist is start guessing, start random walking on the graph and hoping I find it, right? Like that's not a great solution, okay? Well, guess what is the go-to solution in large language model reasoning to this day? But I'll come back to that. But let me share sort of some outcome of this experiment. So you can ask some of these simple sort of path reachability problems to language models. Now, it turns out I'm going to make it even simpler, is that I can simplify the problems to embed some special structure. So it turns out in this instance, I didn't tell you, but I embedded a special structure, which is there is a total linear ordering on the variables, where it turns out that first variable x1, if you assume it has the value true, it will force the next variable to have some value. And that will force the next variable and force the next variable in a linear chain that connects the start variable to the end. So you can solve this problem just by reading off the forced assignments one by one, and it will answer the question for you. So that's what you see on the right here. It's just a sequence of forced assignments that ends up with forcing x6 to be false. Therefore, we know the answer to the question is no. All right. Now, what do the language models do with problems like this? And these are, I've anonymized the models. Sorry, and this is actually, these experiments are back in February, so it's a generation or two behind already anyway. But when you ask the models, questions like this, they're pretty mediocre. They were about 70% accurate, which, chance is 50%. It's something, but these aren't super hard problems. Okay, but look on the right. Okay, the interesting thing on the right is the right is showing the response length. And it's really impressive. It's responding to these questions with like response lengths of 2,000 or more tokens, okay? And you read the responses, it's like total walkabout. Like it might catch a few of the forced assignments and then it's just trying stuff, making mistakes, backing up, I don't know, just meandering. And then 70% of the time landing on a correct answer and 30% of the time landing on an incorrect answer. It's kind of weird, okay? All right, now, let me show you two more things. You can take the same setup, but now you can try to be a little bit more clever, which is, what if you sort of reveal some hidden algorithmic structure to the model? And here I just did this prompt only, but you can do this with supervised tuning as well, is that I just take a bunch of like chain of thought prompts. I just give a bunch of examples, random examples of problems of this form, and just show the linear substitution sequence. Like, here's a problem. Oh, well, if we assume the first variable is true, this variable must be false, so on and so forth, to finally answer the question. Okay, what happens if you kind of prompt or prime the model with these kinds of examples? Well, good news is the models get way better, okay? Up to 90, this is still a little pathetic, but anyway, I'll come back to it. But there's a clear improvement here. But look on the right, the biggest change is the model behaves completely differently. The model now responds without, instead of going walkabout, it responds by simulating the algorithm. It literally implements a forced assignment sequence. It considers the first variable assigned to 2, and then it says, oh, if that's true, this next one must be false, and that must be false and true, and so on. Okay, and it still gets the values wrong, and so on, but it's up to 90%. So the models pick up from sequences implicit algorithmic behavior, especially if that implicit algorithmic behavior is simple. Okay, well, that sounds promising, but that's not the interesting experiment. Okay, the interesting experiment is the next one, which is I can go back to this setup and the exact same kind of problem with a hidden linear substitution sequence. But instead of revealing the sequence in the linear order, what I'm going to do is between the first variable and last variable is I'm going to visit the forced value assignments in a random order, a random permutation of all the variables in between the start and the end. Okay, so for example, here it's saying, if x1 is true, then x7 must be false. Just skip ahead and then skip back to x9 must be false. Just jumping around in this order. Okay, what do you think this does to model performance and model behavior? And I usually have fun with this game, but of course I can't play it here. What it does is, it's not that it stops helping, it's that it destroys the model. The model now basically operates at chance, okay? But if you look on the right, the behavior of the model is the same as the previous case. That is, the model simulates this execution of a forced assignment sequence. It's definitely saying, oh, let's assume that variable is true, and then this variable must be false, and this must be true. Same algorithmic behavior, but all of the values it's guessing are basically random. Okay, what's going on here? What's going on here, at least my intuition is, the problem we're seeing, even in simple linear time problems, is that there are big computational gaps. It turns out the next variable, in the order, has a very simple explanation because you have all of the constraints, all the, the immediate edges. You don't have to do any computation much to figure out, or you could have a constant computational budget to figure out the next forced value. Okay, but when I start skipping around, like if I skip ahead many steps, now I'm asking the model to do a bunch of extra computation that is not in the data. Okay, now think as a human. So, okay, appeal to intuition. You check a proof in a paper, you check a step, yep, 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 and then, whoa, where did this step come from? Okay, we all have this intuition. What do you have to do at this point? If you want to understand that proof, what you, the poor human, have to do is you have to fill in that computational gap yourself. You have to find your own explanation that takes you from the predecessor to the successor. If you cheat and you do not do this, and you say, oh, no, I'm too lazy, I'm just going to memorize this proof, what you are doing is guessing. Okay? And when I give you a new problem where you have to use the same proof technique, you're just guessing, and you're not going to perform well. That's what we're seeing here. When we have computational gaps in data, we're doing supervised fine-tuning or even prompting, we are training the model to guess when the computation involved is greater than its computational budget. The other thing to remind you of is the computational budget per token is one pass through the transformer. That's a constant budget. It's a big circuit, but it's constant. Okay? You are not going to compile linear time algorithms into a constant circuit representation. It is not possible. All right. Okay. How are we doing? Not great. I got stories. I'm going to have to skip some of them. Let me try this story, and then I better do some reinforcement learning stories. Okay. Well, I need this story because it's how I'm going to complain about reinforcement learning. So bear with me. So let's try one other thought experiment, okay? Which is, imagine the world is a big directed graph, okay? Why would you care about a big directed graph? Well, a big directed graph, by the way, is a language model. It's a language model where the context window size is 1. That is, every vertex is a token, the context is a single token that you're looking at, and the edges are a transition from one token to the next token, okay? A real language model is just a hypergraph extension of a directed graph. Okay, but let's take directed graph because it's just going to be much stronger. Our intuitions are going to be much stronger. Hypergraphs are confusing. Okay, in fact, hypergraphs are how we got the Turing completeness proof. But I digress. Okay, imagine I give you a big directed graph. Okay, token to token, and also imagine that the only thing you need to do in life is solve one kind of problem, which is path reachability. The only problem you need to solve is I'll give you a pair of vertices S and T, and you need to find a directed path from S to T in this graph, okay? That's all you got to do, all right? And the question is, how are we going to go about doing this? Now, what I like about this example is it actually separates pre-training from post-training very cleanly. The first thing you're going to need to do to solve a problem like this is you need to know what the graph is. What are the edges in the graph? If you don't know what the graph is, like, you're not going to find paths in the graph. This is what pre-training is for. That's what pre-training does. It's learning the edges in the graph. The other thing to observe is all that pre-training data looks like sequences. It looks like paths, human paths here, there, and everywhere. For pre-training, it's not paths. It's just next token given context. Okay, but if you're just learning the graph, that's awesome. That's probably the right way to go about it. We can get into subtleties about doing better than that. But basically, pre-training, learning the graph from data, that's fine. And frankly, I don't know how much more data we need to really learn that graph. We kind of have the graph, okay? That's not the big problem right now. Or you can spend $18 billion to figure out if that's the problem. But let's, okay. So step one, let's say we have the graph, and it's obviously a weighted graph, right? So for every vertex, there's a conditional distribution over like next reachable vertices. Okay, now let's consider a problem, an algorithmic problem, okay? Which is, finding paths in a graph. And we could think of this as post-training. So we have our big model, it's learned a graph, and now we want to turn that into a policy that can find good paths in a graph, where you give me new ST pairs and it can find that path, okay? A couple of things to observe is the policy is different from the pre-trained model. Obviously, because the policy, as we do any sort of reinforcement learning on the policy, it becomes less stochastic, right? It becomes more and more deterministic. The policy forgets edges in the graph. It should, okay? Post-training is about forgetting all the useless stuff, but it's more than that. It's about sharpening focus on useful algorithmic paths. Okay, so how might we recover a pathfinding algorithm by staring at data? Imagine I give you really interesting data, like I give you a big repository of shortest paths in this graph. I'll give you tens of thousands, millions of paths, okay? Now, the number of possible paths is, exponential in the size of the graph, so that's an inexhaustible supply. But let's say I give you some huge collection of paths in the graph, and you hope that what you're going to do is you're going to post-train. You're going to fine-tune the weights in your language model to turn it into a good path-finding policy. A path-finding policy that on new ST pairs that you never saw in your data, you're going to be able to find shortest or near shortest paths, okay? And what I'm going to declare right now, and I'm going to try to defend, is that this cannot work, okay? And it's not a statistical issue. You can look at ever more paths. You can fit the paths on the training data. You're always going to see out of distribution failures, and you will never solve this with more data coverage. Why would I say that? Because you have to think about this problem as a computer scientist. As a computer scientist, how do you find shortest paths in a graph? Well, mumble, 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 dynamic programming, Dijkstra's algorithm, something, something, okay? But put more intuitively, when you're finding a shortest path in a graph from one vertex to another, the first edge choice is the hardest choice. The first edge choice is the choice where all of the computation is required. Why? Because to know the optimal first edge choice, you need to already know the optimal second edge choice. And to know the optimal second edge choice, you already need to know the third, so on and so forth. It's a dynamic programming problem, okay? And the best known dynamic programming problems for this type of problem is, it's actually not bad. It's super linear, like n log n, like Dijkstra's algorithm. If you use fancy data structures, it'd be quadratic if you're naive, okay? So it's some sort of non-trivial algorithmic problem. So here's the challenge. I'm now going to find a path from S to T using my transformer, okay? That first token I emit is my first edge choice. I have a constant computational budget. But to solve this problem, I need n log n compute. You are never, I repeat, never going to compile an n log n algorithm into a constant compute budget. I don't care how big that constant is. There will always be failures. This cannot work. It's not a machine learning problem. It's not a data coverage problem. This will never go away. Okay? Okay, I feel like I'm hammering this to death, but there. Okay, let me continue. Okay, this cannot work. Okay, here's a paper I have to skip. I like this paper a lot. I like this paper because it was at NeurIPS 2002, which is the NeurIPS where the chain of thought prompting paper came out. It was the NeurIPS where ChatGPT was released, so obviously nobody paid any attention to this paper, but it's kind of nice. It's about learning from traces of actual algorithms instead of hopeless things, and that turns out to be a good idea. But it requires knowledge of a useful algorithm, so boy, Sherry, don't get mad. Anyway, it's a great story. I'll have to tell it another time. Finally, I want to end on hopefully not creating too many enemies, but I want to end on thinking about how RL is addressing these problems, okay? So I'm sorry, it looks like I'm a bit over, but I'll try to wrap this up. Okay, we already know offline learning is limited, and that's actually related to what we've talked about already, so forgive me, everyone, I have to skip this one. But let's cut to the chase. I'm sure you're all well aware right now that like these so-called reasoning models are all the rage, right? And I think you're also well aware that these so-called reasoning models, which are just big LLMs, are post-trained using reinforcement learning, online reinforcement learning. Actually, more to the point, on policy reinforcement learning, okay? And so it seems like problem solved. Reinforcement to the rescue, we're done, okay? A few observations here. First observation is actually It's not really RL that's working. It's literally policy gradient. Now, okay, fancy policy gradient, PPO, GRPO, DAPO, ProRL. There's just this like endless chain of like refinements to policy gradient. But basically, it's on policy, stochastic gradient updates of the expected reward objective, right, expressed over trajectories. And that's interesting, but the history of reinforcement learning research didn't really, I would argue, prepare us for this. At least didn't prepare me, because I was thinking like, wait a second, what about my beloved value functions? What about Bellman consistency? What about all that stuff? Like, that seemed like so right, okay? Doesn't that matter? And I want to sort of address each of these 2 points. So I want to talk about Bellman consistency, and I want to talk about, really, is policy gradient actually working? And then I'll be done, and then you're free. Okay, I'm sorry, I'm over time. Okay, why don't we talk about Bellman? Well, because something's wrong, actually. It's not working, and I'm sorry, right? But honestly, it's been years now, many years. There have been many attempts to get proper RL, like value-based methods, to deliver results on getting LLMs to reason, and it's losing. I'm sorry, it's not me. I'm just the messenger. It's not winning, right? Policy optimization is winning. This is very frustrating, very embarrassing to reinforcement learning researchers embedded in these big tech companies. Okay. What's going on here? Now, I'm going to give 2 answers. The first one is, I think part of it, but it's a small part. I think the real answer is the second one. But to be fair, one answer is actually, I think it's a little bit about this sort of temporal resolution. That is the very concept of a Q function right at the heart of, a lot, not all, but a lot of value-based approaches, is that the concept of a Q function is brilliant, but it's a counterfactual, right? Q of SA literally means if you're in state S, counterfactually, force yourself to take action A for one step and then do whatever after that, okay? But what happens is the size of that step shrinks, okay? In the limit, as that delta t, the size of that step shrinks to 0, the concept of a Q function collapses, right? If I commit to an action for an infinitesimal amount of time, it will have no influence on the future. The whole Q function is flat for any given S. Okay. Now, of course, we're not in a language model. We're not really looking at that. But I've heard a lot of people complain that a per token action value function, they're having a lot of trouble getting this to work. And you can think that, yeah, because these computational sequences are actually very long. And the impact of a single token change on these long sequences where the model can correct and do whatever later, it's infinitesimal. So you're basically trying to estimate a Q function where the entire range of Q values gets in a narrower and narrower tube. And you have to get this infinitesimal decision right over longer and longer horizons. This is super tough, okay? I think we understand this. I think, there's lots of ideas about getting around this. Options being one, but there are many. But this, I think, is part of the challenge. But I'm going to argue, I don't think this is the real challenge. And in keeping with the theme of the talk, I think the real problem is a computer science problem. And maybe you see this coming. The problem is the concept of a value function is based on sort of a temporal consistency property, Bellman consistency, temporal difference consistency, something like that. Which means if I'm using Bellman consistency or temporal consistency to train my model, I am actually training my model to solve the dynamic program. The dynamic program that is either the optimal action values or the dynamic program that is either the policy values, whatever. I am training my model to solve a dynamic programming problem. Now, if I'm training my model to solve a dynamic programming problem on one instance, one model, yeah, this works, okay? But that's not what we're doing with language models. You're training one model to solve all instances, all pathfinding problems, all reasoning problems, the whole world's problems, one model, okay? If you want one model to solve all the problems, now you're in the world of computer science, okay? What is the computational complexity of solving a dynamic programming problem? And I'm here to tell you, it ain't constant, right? It's linear plus plus. So what's going on? When we take our function approximation techniques and we apply it to value-based learning, we are taking our function approximator to try to compile this, ultimately, the solution to this dynamic programming problem into that circuit, but you have a constant compute budget. You cannot compile a superlinear algorithm into a constant compute budget, no matter how hard you try. And so what this creates is what we used to call delusional bias, but what this creates is immense pain. And no amount of replay buffers or augmentations or making the model a little bigger is going to solve the problem of compiling a linear time algorithm or more into a constant compute budget. I don't see this working, okay? Now, forgive me, I'm not trying to be mean here. I'm just trying to think this through, okay? This is my best shot right now at explaining the shortcomings. And I'm going to get kicked off the stage. So let's talk about policy gradient before I get kicked off. So policy gradient's working, right? Well, sorta. But if you really look at this, I mean, okay, so there's some good aspects to policy gradient. The one beautiful thing about policy gradient is all parameter updates are performed on sequences that have no computational gaps by construction, because all of the data sequences are self-generated by the model. The model can absolutely explain that sequence because it generated it. Okay, so this is sound computationally. And so we're just hill climbing on some reward signal on perfectly intact computational sequences that the model has no problem explaining. This is a good idea. Okay, I think it's very sound. And this is working. This is the thing that's behind, sort of the current like reasoning models that are out there, at a high level. But there are many drawbacks here. The first obvious drawback is I don't know how many of you have run these algorithms or tried to do things this way, but they are unbelievably slow. I mean, policy gradient explores at like a snail's pace. It is very dumb exploration. It's very arduous, very slow exploration. It's even worse than that. You may have heard that these reasoning traces are getting longer. Okay, and that's being sold to you like this is a good thing, like more thinking going on. No, it isn't. You know what's going on in these long reasoning chains? More random walk. I'll give you more random walk. The longer you random walk, the greater your chance of stumbling into a solution. And literally, what's going on in these methods is you're biasing a random walk, but really trying to hope that you stumble into a solution. And you're scaling up the length of the walk, and you're slowly changing the distribution of the model, and hopes you get there, and it's doing something. Okay, but this isn't very impressive. So I would argue we are indeed achieving success right now through the pursuit of mediocrity. But that's a good thing. The advantage is we are not pursuing unattainable goals. We are not trying to compile some superlinear algorithmic problem into a constant circuit representation of that algorithm. We are just trying to compile into some constant circuit some very inefficient algorithm, and we're compiling it very inefficiently, and that's what's winning. Okay, so victory, we're done, we can all go home, right? But as a parting shot, I think there are open questions here. So in my mind, the biggest open questions, at least that vex me right now, is, come on. A, we don't want to rely on random walk, but B, we definitely want to improve the efficiency of exploration, but it's subtle. If I start getting fancy and say, I'm going to use Thompson sampling, I love Thompson sampling, or UCT or whatever, you have to be careful because you're now doing a bunch of additional computation that is not showing up in the sequence. You are running a huge risk of training the model to guess, and you are going to be met with disappointment. So being more efficient at exploration while retaining computational integrity, this is an interesting challenge. I have I have some thoughts about this where we have some things in flight, but I think this is open and I think this is pretty critical. And how do we leverage off policy data is another interesting one. I end with an apology. Sorry about the tone of this, but I had to hold the mic up. It's really disconcerting. But the takeaway is quite simple. The only real message I'm trying to say is, yes, machine learning is awesome, reinforcement learning even more so, but computer science matters, especially when you're trying to train LLMs to serve a whole range of problem instances. You are now confronted with the laws of computation, even questions about computability and complexity. And if you as a machine learning researcher ignore those laws, I predict disappointment. And I think this really matters. And this is the main point I'm trying to make. With that, thank you so much for sitting through this. Thanks for all my questions.